This is the part 2 of our first video recording. We're now discussing our static system, linearization of our static system, which is a nonlinear flow like given with that equation. So we will try to linearize it around the operating point P star Q star. Our linear model is actually a line which is tangent at the operating point. We are trying to find the equation of that line. This is linearization. Okay, so this is our pressure drop at our nominal operating point. We find the Q corresponding to that for a given KT. And then we write the Taylor series expansion of Q, which is a function of the pressure. This is Q star plus the derivative of the derivative with respect to pressure at the operating point times del P. That term is our linearized term. The higher order terms is cancelled, as you remember. So we have that equation. So that is our linear model. What is dq by dp? I have to take the derivative of that equation and evaluate this dq by dp, the numeric value of this, at P star. P star is 400 kilopascals. I know KT, so that value is known as a number. So I put it here. So del Q is equal to that number times del P. So this model is valid as long as I'm close to the operating point. Otherwise, the error that I make by linearizing the nonlinear equation will be large away from the operating point. Okay, for dynamic systems, actually, the linearization is a bit more complicated from the static system. Remember, we do the linearization. This is by Taylor series expansion, but this time our function is not a scalar function. It maps the n state variables to an n number of functions. So that is a matrix, remember. And that is also a matrix for input matrix. And they are defined as, this is matrix A. This is the Jacobian, actually. We call this Jacobian of the function with respect to x. And that is the Jacobian of this function with respect to u. And those Jacobians are equal to the A matrix and B matrix. So this is how we make linearization, remember. Again, our perturbation values are the difference, the value of the state minus the nominal value of the state. And similarly for the input, we have the same thing. Okay, we have made an example in the board. Remember, several examples for this. So it must be clear for you. You have to also check the examples in the textbook. Now, because of this virtual education platform, you need the textbook much more than before. So read the textbook and see all the examples by yourself. Okay, input-output equations, remember, we represent the system by our differential equation and put it in the input-output form. An example was a mass spring damper, and that z is the position, this is velocity, and this is the acceleration. If someone says that our output of interest is position, so y is equal to z. We substitute that, then we have this equation. So that is the input-output equation. We use it for single input, single output systems. For MIMO systems, this is a bit complicated. Okay, so we use Laplace transform in order to find the transfer functions, remember. So that was the Laplace transform. And we can use Laplace transformation to transform standard time in functions into Laplace domain, and therefore Laplace tables can be constructed. And transfer functions are commonly used in block diagrams, for example in Simulink and numerical algorithms such as MATLAB and Simulink. So transfer function is a very important milestone, very important part in system representing systems. Okay, how do we develop transfer functions? We have shown that, for example, a third order system, and the input is acting on that third order system by itself and by its derivative as well. Okay, so how do we find the Laplace transform of that? Remember, we assume an input in this form. The output must also be in this form if the system is linear. So that was the way we have found the Laplace transform. So actually, in transfer functions, remember, the initial conditions are always zero. So the Laplace transform of y dot, remember, is this, s times ys. Actually, we have assumed y is equal to e to the st in the form a constant times e to the st. So s times ys e to the st, when we just take that in a parentheses, we find our ys divided by us. So that is the transfer function. Okay, we can analyze dynamic systems using Laplace transform, as we said. So we apply the system's time domain input output equation, the Laplace transform. You can find analyze the system, or we can use the system transfer function. Applying Laplace transform to system's time domain can incorporate non-zero initial conditions, but if you have transfer function, the initial conditions must be zero. So what were the basic steps using Laplace transform method? Take the Laplace transform of every term. It will convert an ordinary differential equation into an algebraic equation in the Laplace variable s. Solve the algebraic expression from step 1 for the Laplace transform of the output of ys, and take the inverse Laplace transform if you would like to see the response in time domain. That is an example. We have such an input-output equation. The initial conditions are given, so that means that we cannot use transfer function approach. We have to solve this differential equation by Laplace transform method without using transfer function. So it's given that the input is a step input. The input value is 4 forever. So take the Laplace transform of each term. You see we have the Laplace transform of y dot is like this. So we have the initial conditions. As they are non-zero, we have to substitute those values to here. And then Laplace transform of the input, which is 4 over s. Remember, the Laplace transform of a step is 1 over s. So combining all the transforms as a single equation, that is the result. So we can solve for the Laplace transform as such. So that is ys. So we can remember, in order to find the inverse Laplace transform of that, we use the method of partial fractions. So I write it in the partial fraction expansion form. I have 3 poles. Remember, the pole of a transfer function was the values of s that makes the denominator equal to 0. So I can solve for a1, a2, and a3 by 3 equations, 3 unknowns, or the method of residues that we have shown and we will shortly review again. So I have found a1, a2, and a3. So that is my solution for in time domain. We finally check whether these are correct. Substitute the initial value, it is -1. So this is correct. For the first time derivative, the initial value y dot 0 is also given. So check whether this is correct. So it checks. In transfer function analysis, derive the system transfer function, multiply the transfer function gs by the Laplace transform of the given input to obtain the Laplace transform of the output, and take the inverse Laplace transform. This is actually very similar to the previous method, but in this case, the initial conditions must be equal to 0. Otherwise, you cannot use transfer functions. For example, in this case, in this equation, actually remember that is very similar to the differential equation representing an RLC circuit. So we take the Laplace transform assuming all the 0 initial conditions, so ys divided by us is equal to this, so that's the transfer function. That transfer function represents only the system, regardless of the input applied. Okay, so that's the system characteristics. So the output is equal to that system characteristics times the input, whatever type the input is. Okay, so transfer functions are limited to LTI systems. Don't forget this. You can never take a transfer function of a linear time varying system or a nonlinear system. So transfer function is a mathematical model of a particular system, and transfer function holds for any input and is unrelated to a particular input function. Many different systems can have identical transfer functions. Remember, I have given you the example in the class. We are making, let's say, an experiment on an airplane where we have an input of, for example, air gust acting on the body and on the fuselage, and we would like to see the vibration of the wing, any wing due to that, but it's very hard to do that experiment in lab. So instead of that, we just prepare an electric circuit having a similar differential equation and do all the experiments based on that. So the important thing is the mathematical model, not the system, the actual system, physical system that you are working on. Actually, in MATLAB, remember, in MATLAB and Simulink, we put transfer functions as block diagrams, as in the simulations. And actually, although those transfer function blocks are in S domain, MATLAB makes the solution in time domain. We will see that in the next part of the course, how MATLAB solves, how do we make simulations using MATLAB codes and preparing Simulink diagrams. Okay, so that was our review for what we have done until now. Actually, we remained on this, the last way to represent a system. It's by block diagrams. Actually, what is a block diagram? They are standard pictorial or graphical representations of interconnected systems. So we just represent a component by a block, usually a transfer function in that block diagram. And blocks are connected by signal paths, which represent the flow of input and output signals, and signal flow into the block represents a mathematical operation, usually a multiplication. And as we will see, Simulink is based on block diagrams, which are constructed from drag and drop menus in the Simulink environment. Okay, we will discuss this in more detail in the next part of the videos.